Here is something a goldfish can do. Recognize its owner.
Hi!
Here is something a crow can do. Recognize a human face. Remember it for years. Hold a grudge. Plan revenge. Crows are doing that right now. Here is something a human toddler can do. Look at a blurry, half-obscured, partially eaten photo of a cat and say,
Cat, cat!
correct. First try. No training, no manual. No one taught them the word pixel. They just knew. Now, here's what a computer, a machine worth millions of dollars, built by the smartest engineers on Earth, could do in the year 2000. Look at that same photo and produce nothing. No answer, no guess. Not even a wrong guess. Just silence. The computational equivalent of a blank stare. A toddler beat a supercomputer. A toddler, who also eats crayons. At some point, a scientist looked at this situation and said,
What if we just showed it every image that has ever existed?
hey, what? The summer project that took 46 years. In 1966, an MIT professor named Seymour Papert had a simple idea. He assigned a student a summer project. The project? Solve computer vision. One student, one summer. It took the entire field of computer science 46 years. To be fair to the student, the problem was slightly harder than advertised. Here's the thing about vision. To a human, a cat is a cat. Sitting.
Cat!
Standing.
Cat!
Upside down, wearing a tiny hat, half behind a couch at 2 a.m.
Cat!
Your brain handles all of this instantly, without effort, without thinking, before coffee. To a computer, a cat is a grid of numbers. Each pixel, a value between 0 and 255. Millions of them. And if the cat moves 1 inch to the left, new grid, different numbers, completely unrecognizable. Different cat. Unknown cat. Threat level, undefined. So scientists did what scientists do when they don't understand something. They wrote rules. Thousands of handcrafted rules. If there are pointy ears and whiskers and fur-like texture, and it's not a dog, which worked, technically, until the cat moved, or the lighting changed, or someone put a hat on it. The rules fell apart every single time. Because the real world does not care about your rules. The real world just keeps putting hats on cats. The woman who decided to label everything. Literally everything. In 2006, a Princeton professor named Fei-Fei Li had a different idea. Not more rules, more examples. Way more examples. All of the examples. Every example that has ever existed. She wanted to build the largest labeled image dataset in human history. Not thousands of images, not hundreds of thousands, millions, across 22,000 categories. She called it ImageNet. When she pitched it to colleagues, she later recalled,
People said, this is a thankless job. Nobody will fund it. Nobody will care about data.
One colleague pulled her aside and said earnestly,
Fei-Fei, this could ruin your career.
which in academia is either a warning or a prophecy, depending on whether you're right. She was right. She built it anyway, using Amazon Mechanical Turk, a platform where you pay strangers on the internet small amounts of money to do repetitive tasks. So essentially, she crowdsourced the foundation of modern AI to people who were probably just trying to pay their Wi-Fi bill. 14 million images, labeled, by hand, one by one.
Dog, cat, chair, spatula, a dog that looks like a mop.
All of it. Somewhere out there, a person labeled 14 million images for a few cents each, and accidentally became one of the most important contributors to the AI revolution, and almost certainly has no idea. The annual Nerd Olympics nobody watched until it changed everything. Starting in 2010, ImageNet ran an annual competition. Teams from universities and labs around the world, all trying to build the best image recognition system. The challenge? Show the AI an image, it guesses what's in it. Simple concept, brutally hard in practice. The winning error rate in 2011 was around 26%, meaning the best AI system in the world got it wrong 1 in 4 times. 1 in 4. For reference, a coin flip is 50%. So the best AI was meaningfully better than guessing randomly. And this was considered excellent.
Progress! A triumph!
Science has a very flexible definition of winning.
2012, the year everything quietly broke. Then came 2012. A team from the University of Toronto submitted an entry, led by a researcher named Geoffrey Hinton. Now, Hinton had spent his entire career working on neural networks, through the AI winters, through the funding cuts, through the years when the mainstream of computer science had essentially declared neural networks a failed experiment. At one point, Hinton described his own position bluntly.
I was working on something most people thought was a waste of time.
He didn't stop. His team built AlexNet, a deep neural network, meaning many layers of artificial neurons stacked on top of each other, trained on all 14 million ImageNet images, and powered by something nobody expected: graphics cards, the chips inside gaming computers, the same hardware a teenager uses to render explosions in Call of Duty at 3 a.m. Turned out those chips were extraordinarily good at the kind of math neural networks need. Nobody planned this. Nobody said, let's build AI on gaming hardware. It just worked. The results were announced. Best teams in the world, 26% error rate. AlexNet, 15%. That is not a small improvement. That is not incremental progress. That is the kind of gap that makes scientists stand up from their chairs mid-presentation. One researcher in the audience later recalled,
There was this silence after the number went up. And then everyone in the room understood. This is a different era.
The judges checked the numbers twice, then a third time. No mistake. Deep learning had arrived. Loudly. Without apologizing. What was actually happening inside AlexNet? A guided tour of something slightly miraculous. Here is the remarkable part. Nobody told AlexNet what to look for. Previous systems had human-written rules. Find edges, find corners, find textures that match fur. AlexNet got no rules, just 14 million images, and labels, and
Figure it out.
so it did. The earliest layers taught themselves to detect basic edges, light to dark, dark to light. Nobody programmed that. The next layers combined those edges into shapes, curves, circles, lines meeting at angles. Still nobody's instructions. By the deeper layers, the network was detecting things like fur texture, eye shape, the specific curve of a dog's ear. Things no engineer specified. Things the network discovered, on its own, from examples. Hinton described what they were seeing with characteristic understatement.
The network was learning features that we didn't put in. It was finding structure in the world by itself.
Which is a very calm sentence, for a very alarming discovery. A machine taught itself to see, the way a child does, except it looked at 14 million images in a weekend. Your child took 3 years to learn the word spoon. No offense. The part where the machine gets better eyes than you. Cool, cool, totally cool. After 2012, the error rate dropped fast. 15%, 10, 7, 5. And then in 2015, a team crossed the line. Error rate, 3.5%. Human error rate on the same test, 5%. The machine was better at seeing than the humans who built it. The eyes that 400 million years of evolution designed and refined and optimized, lost to a graphics card, running math on photos of cats. When this happened, one researcher said, with magnificent restraint,
We should probably start paying close attention to what these systems are capable of.
yes, probably. Starting now would be great. We are fine. Everything is fine. In 1966, a professor thought one student could solve vision in a summer. In 2006, one woman decided to label the entire internet by hand. In 2012, a neural network, trained on those images, powered by gaming hardware, built by a man the field had ignored for decades, quietly rewrote what machines could do.
Fei-Fei Li later said,
ImageNet didn't just change computer vision, it changed what people believed was possible.
that moment in 2012 was when AI finally opened its eyes. Not slowly, not gradually, all at once. And once something can see, it starts noticing everything. And here's the thing about a machine that can see. The next question isn't, what can it look at? The next question is, what can it learn to do with what it sees? Because there are machines out there now that don't just see images, they see the board, they see the game, and they're winning.
Oh, this is going to be a whole thing.